Yes, my name is Fabian Kutschera. I'm a PhD student at Scripps UCSD, and I will talk about how source complexity governs a tsunami generation and give examples from a multiple centroid moment tensor inversion, as well as using dynamic rupture models to inform tsunami simulations. And before I get started, I want to make sure that we are all on the same page when it comes to different tsunami modeling techniques. And in this nice overview by Lauren Abrahams and others, we can see on the left, there are techniques which require two steps. That is first modeling the earthquake and then informing the tsunami simulation. And I think the most common approach here is to use static initial conditions, or also referred to as Okada modeling, using an instantaneous sourcing based on elastic dislocation theory. And the example I'll give later is for the Noto Peninsula earthquake and tsunami using GeoClaw, of course. There are also some other techniques which use the time-dependent output of an earthquake simulation as forcing. And whenever I speak about one-way linked, I mean that we use the time-dependent seafloor deformation, and that can then be used to also inform shallow water equations such as GeoClaw. And then the last approach combines the elastic wave propagation in the solid Earth with oceanic acoustic and the surface gravity wave field all at once. We use SciSol for the fully coupled model, and an example towards the end is the Samos earthquake and tsunami. And each of these modeling techniques, I would say, has its own application. And let's start with the Noto Peninsula event, which ruptured in 2024 across an active nearshore fault system and caused a large tsunami within the Sea of Japan. Here on the left, you can see the first USGS final fault slip model constrained from teleseismic data, and that was available about 2.5 hours after the event, with one major slip patch beneath Noto Peninsula and another slip patch offshore in the northeast. Then here on the right is a vertical displacement observational figure from SAR image analysis and field surveys. We see here along the northwestern coast up to 4.4 meters uplift, also uplifting this port here by nearly 4 meters, and then up to 2.4 meters of uplift towards the northeastern coast. And relatively quick, it was evident that this rupture must have been unusually complex, with fluid migration likely contributing to this complexity. And by now, there are many published models, and one of the earlier ones was Ma et al. Using 3 fault segments and suggesting a slow rupture propagation lasting about 15 to 20 seconds near its hypocenter, with slip exceeding 10 meters in the west, but less slip in the northeast. And the fact that the event was so complex also manifested in terms of the variability of finite fault models. For example, the USGS updated their initial model after 10 days, incorporating additional geodetic data. And here we can see that this model has a great fit to GNSS stations, but we can also see that this offshore slip patch in the northeast has disappeared. So we know that different source models will have different implications for understanding the observed tsunami generation and also in terms of early warning. So we use a different approach to constrain the spatio-temporal rupture evolution first, and that is by using a multiple centroid moment tensor model, where each centroid moment tensor marks the location of a major sub-event and has a scalar seismic moment together with strike, dip, and rake information. We applied this for the Noto Peninsula earthquake and specifically inverted here teleseismic and regional strong motion data, some shown as an example on the right. And the preferred model we obtain is in the middle. I'm saying here preferred because the inversion is in a Bayesian framework, meaning we get all the source uncertainties that come with it and literally thousands of models. But here in this talk, I don't want to speak too much about those uncertainties. Just briefly, the model we get shows 6 sub-events labeled E1 to E6 in time. And we also observe about a 20-second delayed renucleation near the hypocenter, with one sub-event being situated next to E1. In general, the rupture first propagates southwestward, and then we have this second delayed northeastern rupture episode. And as part of the second northeastern rupture episode, the subevents E5 and E6 release about 40% of the total seismic moment. The next step is to construct a fault model and then map the sub-event model to displacement. And that means, we need to assign a fault geometry to each centroid moment tensor. And since the uncertainty estimates for the depth of each sub-event here shown on the right are relatively shallow and quite well constrained, we assume first surface rupture and choose an along dip depth twice its centroid depth and a long strike length constant of 25 kilometers. So this is shown in the video here. This is the constructed fault geometry. Now we can assume a rigidity and use the Okada approach to obtain the vertical surface displacement, and that's shown in panel A, indicating that that the displacement from subevents E5 and E6 is located entirely offshore with a peak uplift of 3.7 meters. This preferred model also aligns with the traces of known fault geometries shown by the green and purple lines. And I should mention that the information about the dip of those mapped faults guided us in our choice how we distinguish the fault and auxiliary plane. However, if that would not be available, that could also be more explored in a probabilistic sense. So now we have the GeoClaw Tsunami simulation sourced by the instantaneous vertical displacement. So you see how the tsunami, which I'll refer to as like the sea surface height anomaly, spreads out through the Japan Sea. We see that the wave crests bend parallel to the coastline due to refraction of the Schrödinger bathymetry. If we look near Noto Peninsula, we see some long-lasting oscillations, likely due to the kind of continental shelf, which is there. So similar to the 2017 Mexico event. And then you notice that there are some black squares in the simulation. Those mark tide gauges, and we can compare the synthetics against the observed tsunami waveforms. First, in terms of arrival time, this histogram in the middle shows the arrival time of the initial tsunami crest observed and the modeled one. And that is captured within 1 to 3.5 minutes. So important aspect for tsunami early warning. Looking at some individual tsunami waveforms, we can also see that the model matches the initial polarity and amplitude with high cross-correlation coefficients of up to 0.9, at least for some of the stations. There are other stations like Fukaura further north, where we are not able to match all the trailing waves that well. And here, Ignacio Sepulveda has shown that the bathymetry uncertainties may affect those trailing waves more than they do the leading wave. Additionally, we did not include any landslide modeling in here, even though there are reports that this has affected the tsunami locally. And some folks have modeled this landslide using a kind of spatially limited normal fault, but I think with GeoClaw that might be a nice addition to that, even though I haven't used it. Okay, I want to make one more point here, because when we construct the complex deformation pattern, we assume surface rupture for each event, but that assumption can actually also be relaxed. And therefore, we adapt an existing source dimension scaling relation for dip slip events. And that graph shows the relation between magnitude and source length, width and area respectively, and the black diamonds mark the 6 sub-events. And we see that the constructed fall dimensions fall within the 95th percentile of the uncertainty ranges, and even more importantly, that 5 out of the 6 sub-events still result in surface breaching slip. However, the along strike length is now variable and typically longer, which in turn means that the peak vertical deformation is reduced by about 40% in this case. And if this model is then used to forward simulate the tsunami, we can see that there's a competing effect of the broader seafloor deformation and reduced peak uplift, at least to some degree, and that those counterbalance each other. So I think I hope I was able to show you that our sub-event model demonstrates that resolving the moment release and associate fault location and first order geometry is critical to inform tsunami response efforts. I should mention in the tsunami wave amplitude map, we see this these orange colors facing or trending towards Kashiwazaki. And without this offshore rupture towards the northeast, the models fail to reproduce the tsunami waveforms. So here you won't see this. The scaling relation multi-CMT model I explained before has it, but we see a few or a bit lower tsunami amplitudes in this part of Noto Peninsula. So to summarize this in one sentence, the multi-event, multi-segment rupture of the Noto Peninsula earthquake governs its tsunami generation, and I encourage you to read more about this by scanning the QR code. And this was a lot about one specific type of source complexity, but there are also other types of source complexity. And those we can see, for example, in these fully coupled simulations. On the left is an example from Lotto and Dunham for a 2D coupled Earth-ocean problem. And here we see the tsunami, including some tsunami dispersion, even though for that we could use a dispersive shallow water equation solver. But then ahead of the tsunami, they are much faster and high amplitude seismic and ocean acoustic waves. And on the right is just another example from simulations offshore Japan. And therefore, now we move over to the other side of the world, to the Aegean Sea, which is subject to extension. And here, the normal faulting Samos earthquake struck in October 2020 and generated a local tsunami, as you can see in the figures or pictures at the top right. The bottom map shows the modeling domain, and I'll show you results which are still a work in progress from this smaller blue domain where the Samos rupture took place. And what we do for this event is we systematically increase the tsunami generation modeling complexity. That means we start at the top left with a finite fault model. Here we choose the one by Plika et al., constrained from local strong motion stations and static GNSS data. This is then used in seisal simulations in what I refer to as kinematic rupture, where we prescribe the spatiotemporal evolution of slip or slip rate. You may notice it's a bit smoother, but one result we get out of this are on-fault stress changes. And these on-fault stress changes can be used to set up a dynamic rupture model where the earthquake dynamics evolve spontaneously based on the model's initial condition. We have different dynamic rupture models, and they differ in their initial stress setup. Here I'm showing you one which kind of bilaterally ruptures and then up dip and towards the west. The final slip distribution of all these models is quite similar, maybe with a bit more near surface slip in the dynamic rupture model. So it's no surprise that if we look at the permanent subsidence from those models, that they show a good agreement. So this would be just applying the Okada approach to the final fault slip model. And the next two snapshots are at the last simulation time step from seisal simulations. Now, this can be used to inform the GeoClaw tsunami simulations, and those are shown in the top row. These are snapshots after 6 minutes. All those simulations have the same bathymetry, and I chose a very high spatial refinement for the GeoClaw simulations of about 50 meters to be comparable to the seisal simulations later. So top left is the instantaneous sourcing based on Okada, and then the middle panel and the right panel are the one-way linked kinematic and dynamic, dynamically sourced tsunami simulations. These are now the corresponding fully coupled seisal simulations. So in the middle again for the kinematic model, on the right for the dynamic model. And just by visually inspecting this, we can see that all of these models share similar large-scale features. That is an initial leading wave drawdown, followed by some peak tsunami crests, and then subtle sea surface depression in between again. You can also notice that at the bottom left, I've annotated the 99.9th percentile of the peak tsunami amplitudes for the initial 6 minutes. And just by looking at those numbers, you may notice that the peak tsunami amplitudes can vary by up to 20%, depending on the modeling approach. And to see the differences better, we can subtract the GeoClaw model from the SciCell model. And while there's no difference for the initial leading wave drawdown, there are some difference following, and those can actually reach up to 0.5 meters in absolute amplitude. So to come to the conclusion here, I've shown you that the source, geometric, or sub-event complexity can govern the tsunami generation. Then we systematically compare complexity in the tsunami generation using Okada, kinematic, and dynamic rupture sources. Here, the peak near-field tsunami amplitudes can vary by up to 20%. I did not speak that much about the computational cost, but I think it may be clear that the one-way linked approaches are computational faster compared to the fully coupled earthquake tsunami approach. So those are very well suited to forecast tsunami arrival and initial wave height, as I've shown you for Noto Peninsula. But the 3D fully coupled models are then needed for a detailed kind of reconstruction in the near field when one would want to differentiate different acoustic, seismic, and the tsunami waves themselves. Thank you.